Okay, everyone, this is section 5.6. In this section, our goal here is to be able to find all real zeros of a polynomial function, where this is where that polynomial hits the x-axis. The rational zero theorem says if a polynomial f of x is in this form and has integer coefficients, then every rational zero of f has the following form. We have a fraction of p over q, where p is a factor of a sub 0, where that's just a constant term that's tacked on the end of the polynomial, and q is in the bottom, which is a factor of a sub n, which is the leading coefficient in that polynomial when it's in standard form. So for example, we're going to list out the possible rational zeros of f using the rational zero theorem here with this polynomial. So first I want to think about my p's, okay? And remember, the p comes from the factors of the constant, and in this case that is 12. So factors that help make 12 can be 1, the positive or negative case can go in the 12. Positive and negative case of 2, positive and negative case of 3, 4 is also a factor in the positive and negative case, positive or negative 6, and positive or negative 12 are all factors of 12 itself, okay? But if we want to look at q, remember that was my factors of my leading coefficient, which is just 1 right now. So the only factors of 1 is just itself, but the positive or negative case. Okay? So if we want p over q, or the possible rational zeros from this polynomial, all I need to do is put p over q. So right now, if that looks like positive or negative 1 over 1, positive or negative 2 over 1, 3 over 1, 4 over 1, 6 over 1, and positive or negative 12 over 1. And again, all I'm doing is put each p value on top of the q value, which is just 1 straight across as a q value. Okay, so if I simplify this, the possible rational zeros are positive or negative 1, positive or negative 2, positive or negative 3, 4, positive or negative 6, and positive or negative 12. So here's my possible rational zeros here. Okay. Let's do another one. We're going to list out the possible rational zeros of f using the rational zero theorem here. So again, we're going to list out our possible factors of p. And again, that's coming from our constant. So if I look out my factors of 10, well, that's 1, 2, 5, and 10 are all factors of 10 in the positive or negative case. And now we're going to look at q, or factors of our leading coefficient. So my factors here are 1, 2, and 4, all in the positive or negative case. Okay, and now we're going to list them out as fractions, p over q. And if we put each p on top of q, that is going to be positive or negative 1. Okay, and then positive or negative 2. Those are both over 1. Positive or negative 5 over 1. Positive or negative 10 over 1. Then we're going to go back to using p as 1 and q as 2. So positive or negative 1 over 2, or 1/2. Positive or negative 1 over 4. And then the 2's over 2's. So 2 over that. And positive and negative 2 over 4. And then we're going to use the 5's with the 2. Then lastly the 10. the 10 out of 2, positive or negative case, and 10 out of 4, positive or negative case. But as you can see, there's some repeated in here. We only want to list them one time. So if I go back through and simplify and only pick out the ones that I only need, that's plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10, plus or minus 1/2, plus or minus a fourth, plus or minus 5/2, and plus or minus 5/4. Those are my possible rational zeros of my polynomial f here. Okay. So the rational zero theorem only lists out only possible zeros. In order to find the actual zeros of a polynomial function f, you have to test values from the list of possible zeros. Okay, you could test a value by evaluating the polynomial f of x using the test value of x. So for example here, we're going to find all real zeros of f of x, and that polynomial here. Okay, so again, what we're going to do is list out our factors p and q. Okay, and so my p here, again, is looking at my factors are 20, so plus or minus 1, plus or minus 2, plus or minus 4, 5, 10, and 20 itself. Then I gotta figure out my q factors, which is just my leading coefficient, which is 1. So my p out of q, or my possible rational zeros, are plus or minus 1, plus or minus 2, plus or minus 4, 5, 10, and 20. So here's what I'm working with here. Okay, so now I'm just going to test some values. Okay, so I'm going to test, maybe looking at the first one, I'm going to test a factor of x minus 1. Okay, and I'm going to test that using polynomial synthetic division. Okay, so I'm going to put the opposite sign, which is 1 on the left side of the L chart. Then I'm going to write down my coefficients, and it's okay, I don't need any placeholder zeros because my polynomial has descending exponents and we're not missing any. Okay, so my coefficients are 1, negative 8, 11, and 20. Drop down the first one. 1 times 1 is 1, and I get negative 7, and I'm adding 11 and negative 7, which gives me 4, and 4 times 1 is 4, and I got 24. Well, since 24 didn't end up being 0, that cannot be a factor of my polynomial, because in order to be a factor, I have to get a 0 back as a remainder. Okay, so this one is not a factor. So I can't use x minus 1. Now I'm maybe going to test the factor x plus 1. Okay, same thing, do the L chart, but flipping the sign on that gives me negative 1, and the same coefficients. So I'm going to drop down my 1 and multiply, gives me negative 1, and negative 9 when I add those. Okay, that gives me 20, and negative 20 makes 0. So since that is 0, that tells me x plus 1 is a factor of that polynomial, because that's my remainder. Here's my constant, my x term, and my x squared term. So if I go and write this out as a factor here, that polynomial, I'm left with x plus 1, and for my synthetic division, I got x squared minus 9x plus 20, as I'm reading these from top to bottom. Okay, if you remember that. Now I guess got to see, can these simplify all the way down now? Well, x plus 1 is okay, but I can actually factor x squared minus 9x plus 20. I could use the x method with that. So a times c, or 1 times 20, is 20, and my b is negative 9. Okay, and I'm trying to make factors that add the negative 9 but multiply to make 20. Okay, well, negative 5 and negative 4 add the negative 9 but multiply to make 20. And my a in this case is 1, so I'm just putting 1x on top. So x plus 1, x minus 5 is a factor now, and x minus 4. So that's factored down all the way completely of that polynomial, but we're not wanting that. We're wanting the zeros, okay, the actual zeros from this polynomial. So we know that if we set these equal, each factor, to 0, we can figure out what these x values are that are the real zeros or roots of this polynomial. So if I move 1 over here to the other side, x will be -1. Oops. And that was true because we tested that out with polynomial synthetic division. If I add 5 over here, 5 is a root. And if I add 4 to the other side, 4 is also a possible, or an actual real zero of this polynomial. So I have 3 real zeros here. -1, 5, and 4. Okay. And our last example here, we're going to do the same thing, but with this polynomial. Okay, so again, we want to figure out our factors p of the constant, which is positive or -1, 2, 3, 4, 6, and 12 itself. Then our q, remember, is our leading coefficients factors in standard form. Well, that's 10 right now, so plus or minus 1, 2, 5, and 10. Okay, and now if we want the possible, we gotta stack p over q, so that will give us positive or -1, 2, 3, 4, 6, and 12. Okay, and then if we look at a half, a fifth, a tenth, okay, and then starting with the 2, 2/5, and we go to the 3, 3/2, 3/5, 3/10, and if we move on to the 4, 4/5, moving on to the 6, 6/5, and then finally the 12, 12/5. And these are all simplified. I don't need to go through and simplify them anymore like we did in the last one there. Okay, so here's our possible real zeros here. Okay, and again, we need to test them, but there's a lot here. So what I'm going to do is go to my graph, and you guys could do that in the graphing calculator by typing this polynomial into y equals, but I already graphed it here on Desmos. And here, if I look here, my zeros, or where they're touching the x-axis, looks in between -1 and -2, between 0 and -1, okay, 0 and 1, and 2 and 3. So if I go back over to my notes here, we're going to pick out the ones that are lying close to that. So I'm going to try from the graph. We're going to test the values -3.5, which was between -1 and -2. Or sorry, yes, -1 and -2. And then we're going to test -1/2. And we're going to guess 3/5 because that was in between 0 and 1. And then finally 12/5 since that was in between 2 and 3. So if I go ahead and try to test -3/2, which would have been +3/2, because again, I want the flip sign of it. And again, my coefficients, I'm going to write up top, and it's already going in descending order of exponents, and I'm not missing any, so I can just go ahead and fill them in. So 10, -11, -42, 7, and 12. Okay. So now, I'm just going to do my synthetic division of multiply. That will make negative 26 here, and 39, which makes negative 3, and 9 halves, 23 halves, negative 69 over 4, and when we add those, we get negative 21 over 4. And since that's not 0, that means that this cannot be a factor. So negative 3 halves is not a factor, or x plus 3 halves is not a factor. So that one's out of question. But what if we test negative a half, okay, which would be x plus a half as a factor. And again, we're going to do the same coefficients, 10, negative 11, negative 42, 7, and 12. I'm going to drop down 10. Half 10 is negative 5. And I'm adding here to make negative 15, or 16, excuse me. Half of negative 16 is negative 8, and that would make negative 50. Oops, excuse me, that's not negative 8, it's positive 8. Because when you multiply, it makes it positive. Negative 42 plus 8 now is negative 34. Half of that will give you 17, which gets you 24, and half of negative 1/2 of 24 is negative 12, which makes 0. And since that is 0, that means x plus a half, or x value of negative 1/2, is a 0. Okay, so if I go back up here, if I try to make a polynomial out of this, x plus 1/2 is a factor, because we just tested it, and we're left with, if you remember, the remainder constant, x term, x squared, and x to the third power. So we're left with 10 x to the third power minus 16 x squared minus 34 plus 24. Okay, and now I want to see, can that second factor, can I pull anything out of that? Okay, out of all 4 of those terms. Well, I can, because they're all even. Okay, so I'm going to pull a 2 out of all of those. So x plus 1/2, and then I'm pulling the 2 out, so I'm left with 5x to the third minus 8x squared minus 17x plus 12. And I could simplify that 2 times x plus 1/2, that's just going to give me 2x plus 1 times this stuff. Okay. And now we're going to see, can that second polynomial there, 5x to the third minus 8x squared minus 17x plus 12, can that reduce? Okay. And again, we're going to take our p and q here. So the second round of p and q. Well, my p in this case is 12, so plus or minus 1, 2, 3, 4, 6, and 12. And my q is my leading coefficient here of 5, so plus or minus 1, and 5 here. Okay, and now if I make p out of q, the possible zeros of that, I get positive or negative 1, 2, 3, 4, 6, 12, 1/5, 2/5, 3/5, 4/5, 6/5 and 12/5. Okay, so here's my possible zeros here of this polynomial here. And if we were to graph that, again, that polynomial 5x to the third minus 8x squared minus 17x plus 12, if we were to graph that, the possible root or x value or 0 that was in common with that original polynomial, okay, or f of x, is 3/5. So in between 0 and 1 there. So we're actually going to test 3/5, okay? And since it's already 3/5, we are going to pull that out of there. Okay, so with 3/5, we're going to test it as x minus 3/5. Okay, and we have all of the coefficients there. And if I drop down that first 5, 3/5 times 5 is 3. And when I add -8 to that, that'll give me -3. And -20 times 3/5 is -12. And I do get 0. So this one does work as a fact 3/5. That was my constant. Oops. My x term and my x squared term. So when I pulled that out from this given info, okay, I'm left with that 2x plus 1. It's not going anywhere. We just figured out x minus 3/5 is a factor. And then finally 5x squared minus 5x minus 20, coming from this stuff down here when I read it from top to bottom. Okay, so now you just got to see, can 5x squared minus 5x minus 20, can that factor? Turns out if you try to do the x method, it will not factor nicely. But if I look across here at my coefficients, I can pull out a 5. Okay, so 2x plus 1, x minus 3/5, pulled out a 5, and I'm left with x squared minus x minus 4. And I could just simplify that x minus 3/5 times 5, so 2x plus 1, and then 5x minus 3 there, times x squared minus x minus 4. Alright, and again, I could try to use the x method to see if x squared minus x minus 4 can factor apart. Well, using the x method, it cannot, so we can just result to the quadratic formula. Okay, so using that quadratic formula there, and sorry that I'm running out of room. Okay, my a is 1, my b is -1, and my c is -4. So I got 1 plus or minus -1 squared minus 4 times 1 times -4, all over 2 times 1. So I got 1 plus or minus 1, or -1 squared is 1, and then plus 16, because -4 times 1 times -4 is 16. So 1 plus 16 is square root of 17, all over 2, and that actually cannot reduce. Okay, so another factor here is the 2x plus 1, 5x minus 3, and then x minus 1 plus or minus square root of 17 all over 2. Okay, And as we figure out the actual zeros of that, remember we set each factor equal to 0, so 2x plus 1 equals 0. That gave us negative 1/2 that we got from that factor earlier. Then if we do the other one here, 5x minus 3 equals 0. X will be 3/2, and that was a factor x value that we got earlier. And then coming from the quadratic formula, we got another factor to be x equals 1 plus square root of 17 over 2. And that should be a 2. Or 7, sorry. So there's another one. And last but not least, x equals 1 minus square root of 17 over 2. So here's our last one there. So there's 4 actual zeros coming from this polynomial that we just found using the rational zero theorem, synthetic polynomial division, and factoring there.